Today we're discussing automated testing. It's one of the more advanced topics, and here the idea is that we're gonna look at large bodies of source code and trying to get rid of as many bugs as possible. So it's a rather complex, a rather broad topic, but it's also a very important topic when you're looking at different kind of bugs and vulnerabilities that are present in software. One thing that you can take with you is that software will always have bugs and vulnerabilities, and we're trying to get rid of as many of them as possible. Right? So that's the key goal of automated testing. Try to remove bugs before they can do any harm. And our goal is to find and fix them before they are being deployed at the user, and ideally before they can be exploited. So learning goals for today is to differentiate between different testing approaches and also get a feeling of how well they scale and also what their limitations are. We're looking at manual, semi-automatic, and automatic testing in general, with a couple of examples, and then we're going to dive into fuzzing as a modern software testing technique with a bit more detail. We're going to look into input generation, mutation algorithms, and whatnot for different kind of inputs, and especially when you're looking at complex software, the input formats can be arbitrarily complex. And we're going to try to explore them a bit and automate how they can be analyzed, assessed, and whatnot. We're going to look into sanitization methods to detect more bugs because crashes alone are not sufficient, and then potentially identify ways to improve fuzzers. Just for context, right, guarding the software supply chain is key. We've already looked a little bit at the lib/LZMA or XZ supply chain attack, where essentially all the software that you are using in your program, or all the source code that you are using in your program, and all the dependencies that you're using in your program increase your attack surface. Anything that is reachable from your program is part of the attack surface. And with this lib/LZMA supply chain attack, an attacker injected backdoor into lib/LZMA, which is a compression library, right? It has nothing to do with OpenSSH. But it was used as a library by OpenSSH and has allowed attackers to gain root access on affected machines that were linking this library. Now, the backdoor overwrote certain functionality of OpenSSH that then allowed the attacker to trigger an alternate login with a backdoor. Right? So it's made this a new and interesting angle. It was extremely well hidden, extremely well designed, and very hard to find and fix. So what you're essentially seeing here is that there's, even in large browser systems like Google Chrome, there's dependencies and lots of external dependencies. And about a third of the source code in Chrome, or even more, is used for third-party libraries. And vulnerabilities in these third-party components can propagate to the browser and even make it exploitable. In this example here, a bug in a third-party component corrupts memory in the renderer process. So there's a heap buffer overflow in libaviv, which is a video codec that allowed the attacker arbitrary write and then gain code execution inside the render process, which the attacker could then have used to escalate their privileges further. And the Google Chrome security team actually awarded $7,000 for this bug report. Now, even though the source code is not Google's source code, Google actually paid money to the developer that discovered this bug because it was reachable from Google code. Right? Which is fairly an interesting angle. So you can make money by reporting bugs to Google that are not even in Google code. So that's just one example, but there's other examples as well, right? Even end-day vulnerabilities can result in bug bounty payouts. So the Chrome team in this example here awarded $1,000 to a bug for a bug that was reported that was already fixed upstream. So the Google team, the Chromium team, forgot to update the software that they were using, one of the dependencies, and the dependency still contained a bug. right? So even if you're using an external library, you have to stay up to date with this external library. And if this external library is being updated, you need to update your copy of the external library as well, because otherwise you may be exposed to an exploitable bug. Right? And in this example here, the developer from SAP noticed that in one of their systems, when they were looking at dependencies, that Google Chrome didn't update one of the libraries, reported it, and therefore got some money for it. Now, just this as a little bit of context all around it, you may wonder why we need testing at all, right? Or what the need of testing is. We are perfect programmers. We go through a computer science curriculum. Afterwards, we're not going to write any bugs, right? So we don't need testing. Well, maybe you, but I at least know that for the code that I write, I do need testing because I make mistakes. I misunderstand dependencies between different modules. I may misunderstand how the API is being used. Right? So testing is the process of analyzing a program to find errors. And here the goal is to look at the source code, look at it from different perspectives, and then decide if it is following the specification. And in the end, an error is some form of deviation between the observed behavior of what the program actually does and the specified behavior, as in a violation of the underlying specification. And the specification can have many different forms. For example, we can have functional requirements. So the software is supposed to have features A, B, C, and D. As in, it's supposed to have certain properties. It should be able to open JSON files, Markdown files, XML files, whatnot. But maybe it doesn't support XML files of a certain format and just errors out. Right? So this is a functionality violation. And we can detect this violation by comparing the specification of the software with what it actually does. Right? So C testing is some form of testing where we're looking at things. This is what it's supposed to do, and this is what it actually does. So we're comparing two different things. Another angle may be operational requirements, such as if I load this beautiful file in my browser or in my text editor, it should only take a second or two to respond. But if I open a 10 gigabyte file, it may take a minute and use all the memory of my system before the file is actually being loaded, right? So this could be a performance requirement that even I should be able to work even with large files and scroll so that it holds a partial buffer or one. Or usability, right? It's supposed to allow screen readers or people with vision impairments or whatnot to still use the software. Now for security requirements, it's fairly difficult to specify concrete security requirements. Like security requirements can be fairly abstract, such as we should not be able to log in or carry out administrator functionality when we're not logged in as an administrator. So this already depends on the definition of an administrator role, authentication, testing of what privileged functionality is, and so on. But it could also be the program just shouldn't crash on random input. Right? So it's a very simple property. But it's kind of challenging to define these different properties, and especially for security properties. Now, one of the difficulty for security properties is that it requires a logical for-all quantifier, right? So we actually satisfy security guarantees if for all inputs the program doesn't crash or does not trigger an exploitable bug. Now, for all quantifiers, if you remember your logic classes, are very hard to prove. Because now you need to reason about all possible inputs to the program. To give a guarantee that your program does not have any security bugs, you must demonstrate that for all possible inputs that can be sent to the program, it does not crash, which is fairly extensive and pretty hard to satisfy, especially if, let's say, your program reads in a 400 megabyte video file. Right? So this makes this fairly challenging. Now, Edgar Dijkstra already said, testing can only show the presence of bugs, never their absence, precisely due to this reason. Right? We can test and show that, hey, it works as we specified, but we cannot show that there's not going to be any bugs. Right? When we run a test case, if the program crashes, we know that, hey, this is a bug in the program. But we will never be able to demonstrate that for all inputs, the program will never crash. Now, the successful test finds a deviation of some form. And testing is a form of program analysis, where we analyze the code, the testing environment can observe the behavior of the code, and then we're going to try to detect violations of any form. Now, there are certain issues that we are facing with in current software. And there's bugs in all the different layers that we can look at. Bugs can be in the code bases themselves. And code bases are becoming incredibly big and ridiculously big, to say so. So if you look at Google Chrome, that's around 30 million lines of code, or 40 million lines of code, plus external dependencies. The Linux kernel is another 20 million lines of code. GNOME, the user interface, is about 5 million lines of code. Right? So this is incredibly complex, and we're throwing around millions of lines of code as if it were nothing. And millions of lines of code will always have bugs, right, and result in a huge attack surface. Also, a lot of systems are running the same code, which means they're vulnerable and bugs can become weaponizable. As in, if you develop a bug for a piece of software, such as Android 12, you can scale this out to billions of devices, right, and attack billions of devices at the same time. Now, it's a very large attack surface that we're looking at. But also there's dependency inflation, right? So modern programming styles require you to reuse a lot of the components that have already been developed, which on one hand is great, because somebody else is responsible to develop the functionality. But on the other hand, you may depend on one software, on one library that depends on another library, on another library, on another library. And for example, if you're working with PyPy, like Python packages or NPM packages or other kind of packages, oftentimes you're pulling in hundreds of dependencies that you're now just integrating into your project. And all the code that you're pulling in runs at the same privileges as the main application. And with these large amount of dependencies, this becomes a huge risk, because you're trusting all the code that you're including, even if it is being developed by this one person that lives somewhere in Nebraska who has been maintaining it for the last 20 plus years, right? So there's a lot of potential issues of inflating all these dependencies that we're looking at. Same as with system abstraction, right? When we are writing a library that can be used by other components, we may be unaware of what kind of data is being pasted into it, right? So developers may be unaware of the underlying assumptions. Is this running on a mobile system where the power may suddenly go out? Is this running on a large-scale cluster? Is this running on a GPU? Is this running with perfect hardware guarantees? Is this running under some other setting where an adversary can send random data to it, right? So there's a lot of different abstracts here. And also we're seeing more and more is ChatGPT-generated code, which is also adding to this picture. Google recently announced that they are writing 25% of code using AI systems. Right? So only 75% of the code that they are writing is created by humans. And this is somewhat worrisome. And the question is, who's going to be the better developer, the human or the AI system? Quick poll or quick question. What kind of code do you think the Google AI systems will write? Or first, any thoughts on 25% of code are being written by an AI system? Is this good? Is this bad? Yeah?
Probably most of it is just like auto-completing, so that the program wants to write something, the program appears without complete, and Google counts that as code written by the AI, even though it's like the actual intention was in the programmer.
So one hypothesis is that Google just counts all the autocomplete, like of a smart code assistant that just autofills, like Copilot. This could be the case. So your hypothesis is that the code that is being autocomplete could easily be done by a human, but it's just cumbersome and it fills in boilerplate. Are you a Java programmer?
Yes.
So maybe for these kind of environments it's possible. Yeah? Other thoughts? Yeah?
I think it depends on who's using it. If it's an experienced senior developer, he's going to use it more as a helper and he's going to be able to understand what's going on. If it's a junior developer who just asks ChatGPT to do something, and he won't be able to really know what's happening.
So you're saying that the ultimate responsibility still lies on the human that kind of steers this AI system to create better code. Okay, cool. Yeah, I would hope so. What else? Other thoughts? So we have one vote on just autofill or autocomplete. What other code could an AI system create? Yeah?
I feel like it does pretty well with creating unit tests, like for testing. Sometimes you don't think about all the possible inputs just because you just
Yeah.
think about it. And it does pretty well for creating good like edge cases and finding them.
This would have been my guess. Like when I read the article, everybody was like, the security universe was like, oh, well, this is going to be so shitty code, it's going to be so bad. My first thought when I read the original source article was like, they're writing unit tests automatically. Maybe even with a programmer in the loop that just reviews the unit tests in the end. Because unit tests, like it's key to have unit tests, but they are extremely boring to write. Like, who wrote unit tests for your software? Who was forced to write Unicodes for your software? Who enjoyed writing Unicodes for your software? Okay, right, so you're being forced to write if those that were writing unit tests were forced to write unit tests, nobody enjoyed it. Right, unit tests are very, very boring to write. But it's fairly easy to automate, so I think automation is a large part here. And if an AI system automates my unit tests, I'll be very, very happy. And this will give us better test coverage and could in the end actually be a positive step for security. Cool. Last point on this slide, right? There's also integration, possible integration issues. When two systems are being connected, even if the two systems are correct or bug-free, the interaction between the two systems can be buggy, right? So there could be issues with the API that you're using where you're violating some form of API. We're going to look into 3 different forms of testing and validation. Manual testing, such as for code reviews, unit and regression tests, and other different angles. Then semi-automated testing, for example, through annotation, type checking, and dependent types, code bug patterns, searches, and so on. And then we're going to spend some time on automated testing for static analysis and dynamic analysis, such as fuzzing or symbolic execution. And we're going to start with manual testing. Manual testing involves a human developer somewhere in the loop and can have different aspects, different goals and whatnot. And we're trying to highlight some of the different angles a little bit more. Essentially, a lot of the manual testing focuses around code reviews. And code reviews can improve software quality through peer review because multiple people are staring at the code until the bug jumps at them. And then they can hopefully find the flaws and highlight different kind of code smells to tell the developer, hey, you should really fix this. So a flaw is a violation of a specification or a bug. That's a software flaw. And a code smell is not really an issue, but it could become one or could be an issue. As in convoluted code, ugly, missing documentation, or documentation that is different from what the code actually does. Right? These are considered code smells. Right? The code smells a bit bad. Right? But it's not necessarily a bug by itself, but it's somewhat weird, right? So it's not a bug, but it could lead to a bug due to misunderstanding or uncertainty or lack of clarity. The goal of code reviews is to improve code quality, find flaws, some kind of learning and knowledge transfer. Like if you have a new junior developer in your team, the very first thing you do is you give them a couple of thousand files to review and read through code, and this gets them quickly up to speed and make sure they're going to be burnt out after the first couple of weeks in the job. But it's a nice way to transfer at least some knowledge and to talk to them, kidding aside, have them a bit like dive into the different source repositories and get some understandings of the trade-offs and whatnot. Code review can never find all flaws. Why?
Because there are also people who review the code are also
Humans are faulty, right? There may be a bug in front of the screen. Yeah, that. What else? Yeah.
We cannot explore all the paths.
We cannot explore all the paths, right? So we cannot think of all the possible paths that input could flow through the program, right? We may not even know where the library is being used, right? So the library could be used somewhere else if you're looking at a library component, right? We do have abstraction, we do have other kind of approaches to handle complexity, but this also means that we don't necessarily know all the different situations how the code will actually be used. So code reviews are always limited, right? They are never complete. Right? If you think about it, a code review cannot give you complete certainty. There's different types of code reviews. One of them is inspection. Inspection is the most thorough code review. Right? During an inspection, a group of reviewers goes through all code line by line to find flaws and to document any kind of unexpected behavior. So there's multiple developers involved that thoroughly review the code up to a certain time budget. All interactions with the dependencies are inspected as far as the developers know. It validates the current snapshot of the code base, which also means that as soon as you change any line of code, you have to redo the inspection, right? So any kind of code review you're doing on the current version of the code. On Linux, I mentioned 20 million lines of code, right? There's around 400,000 lines of code that are being changed each year. That's more than a human can review, right? So any kind of code review only looks at the status quo, at the current snapshot of the code that you're looking at. Inspection is some kind of stop the world and make sure that there's no concurrent progress, right? Until the validation is finished, they have an exclusive lock on the deployment. Development, and code is not going to be updated. It's the most thorough form of code review, but also very, very expensive because it stops the world, no new features are being implemented, and a lot of developers are working through it. The idea here is that you sporadically check and review all code to make sure that you have very high coding standards. This is done in, for example, high security environments to make sure that the code is safe and sound, or as safe and sound as it can be through code review. Now, a slightly weaker form of code review is a walkthrough. In a walkthrough, whenever a new feature is available, you check that feature. So you're only looking at the feature itself, and then you look at all the interactions this feature has with the rest of the code base. Right? So you look at the feature itself, you thoroughly review the feature, and then you check all possible interactions of that feature with the rest of the system. Code is reviewed incrementally whenever a new feature becomes available, and it assumes that the rest of the code is correct, or at least remains correct, somewhat. It allows gradual review of the code base, focusing on new code that is being added. So this allows, for example, to review changes such as pull requests or commits before they are being integrated into the code base. Fits fairly well to modern development, and this kind of pioneered in the early 2000s with Google's code review practices that are very well documented and were considered like a high-cost operation at the time, but it now shows that the code quality improves quite a bit and potentially saves quite a bit of money due to the cost of fixing bugs downstreams. One of the benefits of doing walkthroughs with the developers that are involved in the development is that they already know the source code, right? So the context switch of switching to a large new code base and actually getting familiar with the code base is much lower if you're doing a walkthrough, because the developers will already be somewhat familiar with it. The risk is that the developers may be blind to any kind of things that the code misses. Right? If you think that the code can only be called in this under this certain behavior, you may be missing an alternate way that or a bug that you have programmed. There's a slight trade-off there. The goal of walkthroughs is to continuously validate code as it is integrated. So less thorough than inspection, but still fairly reasonable, allowing gradual deployment and development. The least precise form of code review is an audit. An audit is a group of reviewers that spot check the code to find flaws. They often look for patterns to find flaws or violations. An audit is what you usually do if you've been hacked and all your data has been sold on the dark net, and you're trying to get regain trust in your user base. An audit is it's somewhat related to a smell test, so it's not very thorough, because usually if you're hiring an external company, you're hiring them for 50 hours or 100 hours of code review, and then they're going to write the report. Right? So audits do not replace walkthroughs or inspections. An audit is a bit of a smell test. Right? If in an audit they find 50 issues that you need to fix, your code quality is going to be pretty bad. But then if the audit doesn't really find as much, it doesn't really tell you that the rest of the code is safe. Right? Due to the audits are very, very spotty. So you embrace incompleteness on that. Here, the idea is to get somewhat of an overview of the code quality and to identify some of the bigger flaws, right? The main risks, the main potential issues that this code could have in a short amount of time, right? If you're new on a code base, you're often trying an audit, you're spot checking certain parts, and then trying to figure out how different things fit together. Cool. Moving up a bit on the abstraction chain are unit and regression tests. We already talked a little bit about unit tests before. Hopefully they are being written by AI systems going forward. A unit test essentially takes a code fragment, a function, a file, or a small module, and runs a bunch of tests on it. And unit tests are a nice way for a developer to encode their constraints. Like, I assume that my compression library will always be run with arrays this size, that functionality, correctly terminated or whatnot. And in a unit test, you can actually specify, this is the input that I send into my program, this is what I expect. Right, so as a developer, you're expected to write hundreds of unit tests that check individual bits of functionality in your code. There's both positive tests to ensure that your code accepts and correctly processes valid inputs, and negative tests where your code rejects invalid inputs with an error message, with terminating the application and whatnot. A good thing is the more unit tests you develop, right? Whenever code is changed, you can rerun the unit tests to also protect against regression. Do you know what regression is, or a regression bug is? What's a regression bug? Yeah?
Something that works before, now it's working anymore.
So a regression bug is you're going back, you're fixing a bug. You fixed a bug at one point in time, but then the bug is being re-added. So you're regressing to an earlier state where software did not work, right? So you're going back to an earlier state where software was faulty. And this can happen, for example, you're fixing a bug, you're creating a patch, you're submitting it, and sometime later down the road, somebody figures, oh, you broke my feature. and they're changing your patch without knowing about the bug that you fixed and potentially reintroduce the bug. This would be a bug regression for a feature, right? You're fixing a feature, but somebody else changes something else, and the feature is broken again, right? So regression can go both ways. Good. So these unit and regression tests are pushing us somewhat already up the stack towards semi-automated testing, right? With semi-automated testing, we're kind of automating the testing of the software and are trying to use tools that help us to tell us, hey, there's issues in your code here and there. And what kind of semi-automated testing systems do you guys know? What could be a semi-automated testing system? What's better than unit tests? Or more automated than unit tests? I bet all of you have run several of them before. Yeah? You could use an AI to generate unit tests. I would call this fully automated testing. We'll get there in a bit. Good idea, though. What else? Yeah? Integration testing, yes, that's one thing. Not something that everybody has used, I think, but definitely something that can be added there. Yeah?
I haven't used it myself, but
fuzzing, that's automated. Yeah, automated testing. Yeah?
Checking whether it builds or compiles?
Checking whether it builds or compiles. Yes, it's a very easy test, right? It compiles, you're done, right? It's not the best oracle, but it is an oracle. If it doesn't compile, it cannot run, right? So that's a very simple test. What's a bit more generic than that? Compile time warnings, right? That could be a very simple analysis. The compiler will tell you if it thinks stuff is broken. And compilers have evolved quite a bit and now have a massive amount of warnings that they spit out during the compilation of your code. Highlights issues in code and gives feedback to developers. And especially Clang and the LLVM framework made huge progress in compiler warnings and compiler errors. GCC was very shitty with warnings, so it didn't give good warning messages, but Clang is fairly extensive. These compile time warnings must be very, very low overhead and extremely simple to run. They are usually like there's the syntax errors, right? If you forget the semicolon or you don't have the right format, the compiler will yell at you to fix it. So that's one part. That's the simplest part as part of parsing. But assuming that you get parsing correct, the compiler can also check types, can analyze there's some dependencies, lifetime of variables to some extent, scopes and whatnot. So there's a bunch of different things that compilers can actually do at fairly decent precision. And this is like a form of a static analysis that is extremely simple to run, and it scales to millions of lines of code, right? It scales to pretty much all the code that we can compile and run, right? So this is like the basic static analysis we can look at. If you want to have a fairly decent amount of checks, you have to tell Clang W all, W extra, and W pedantic, because these kind of warning levels evolved. And people didn't want to go back and just add more and more. Like, for example, W all enables a set of like 30, 40 different warnings or types of warnings. Mostly easy to fix. Extra extends W all with a little bit more detail, for example, empty function bodies, unused parameters, or different kind of sign mismatches if you have unsigned integers or whatnot that you're using. Pedantic then goes one level deeper, beyond strict C and C++ and highlights areas of code, bad code style and whatnot as well. And everything turns on every single warning that exists and often adds a lot of noise, especially if you're working on older code bases. This gives you just like a very long wall of potential issues and errors that you have to look through. And as these evolved, you can play with the different warning levels and see what your how good your code actually looks. Right. Static analysis are kind of the extension of compiler analysis. And a static analysis reasons about the code instead of executing it. So think of this as an abstract interpretation of the code. It takes the code, translates it somehow, and then runs an analysis or a test on the code itself without executing the code. So it doesn't run concrete input on it. And the line between static and dynamic analysis is a bit blurry, and we'll discuss this in a bit when we go into symbolic execution. In general, a static analysis looks only at the code without keeping track of concrete values during the execution. The benefit of static analysis is you get full coverage, right? You can reason about all the source codes that you're looking at. So there's no need for 2 billion unit tests that execute every single line of code. You can just run all the code through your static analysis. It scales to very large code bases, but the test cases may miss certain edge cases. Because you don't keep track of values of variables, you cannot look at value dependencies. For example, if there's the exclusive ifs that check different values, the static analysis will have a hard time distinguishing those. Disadvantages are that the computation depends on data, resulting in undecidability, so you can never find all bugs, and the over-approximation may result in false positives. As in, the static analysis may report a bug even though there is no bug, right? Due to lack of information. It doesn't have any kind of runtime information. It doesn't know what the concrete types of the variables are that you're looking at. Thereby, it may run into different kind of issues there. I very highly recommend you the article that I linked down here, A Few Billion Lines of Code Later, which is a very cool article, still holds true, about deploying static analysis to find real-world bugs. And especially on the development of such a static analysis engine compared to writing a research paper. Where in a research paper, it's more, at least in the software engineering world, it's more about the idea how this could be used to find a bug. Here, it's also actually deploying this in practice and running this on a customer's the CI/CD system without deleting all their code in their weird compilation environment, in their weird settings and whatnot. So all the different things that we academics usually just ignore. So it's a very, very interesting article that I really enjoyed reading. Annotations are the next step up, right? So if we involve the developers, we can actually have them look at the code and be a bit more informative about it. And annotations augment the source code. So they're not being used during compilation. The compiler doesn't care, right, about the annotations you add. But you can encode all the different heuristics, assumptions, preconditions, postconditions, using annotations in your code. And then your static analysis system can check for violations of these annotations and thereby validate that certain properties are actually true. Annotations, for example, would be types in Python. That's one example. Argument usage in C and C++, which arguments are being used, how they're being used, and whatnot. And pre- and post conditions for different kind of verification. So they give you a little bit of more control of the source code. One of the difficulties here is with annotations, same as with static analysis as before, is if you're working on an existing source code, there's going to be 4 billion error messages or warnings that's going to be very, very hard to work through. So the biggest issue with these static analysis is that the false positives are going to result in very quick warning fatigue, where developers will have a hard time differentiating between true positives and false positives. Also, false positives rates are often 70, 80, 90% in source code, which is crazy, crazy high and can be much higher than that, right? So you have to analyze 10, 20, 30 warnings before you find a true bug. And developers get fatigued and have finite resources. So you have to figure out if this is a reasonable way for them to spend their time. I want to talk about two static analysis tools that are being used and deployed: CodeQL and SemGrep. CodeQL is a static analysis framework that finds bugs where you can define patterns. So the idea here is that CodeQL takes your source code, compiles it to detect to create control flow graphs, detect type issues, type inheritance chains and whatnot. And then you as a programmer, you can define patterns that define how a bug looks like, and then CodeQL runs this pattern on the source code that you just compiled and then tells you, hey, I found a violation about this issue. Right? So here, this analysis that we're showing here from field F, the field that we are looking at is public but not final, and then we select declaring type and whatnot and issue a potential warning. Right? So these issues, these queries are heuristics that kind of encode how bugs or bug patterns look like. The advantage of CodeQL is that we get type information, maybe even control flow information about caller-callee relationship or whatnot to a certain extent because of aliasing, but at least this gives us somewhat details. But it's fairly expensive to create this database. Running CodeQL on Chrome takes about 7 hours just to compile the Chrome source space, and then you need to issue the additional queries on top. An alternative to CodeQL is SemGrep, where you can similarly encode source code patterns in a much more lightweight manner. So similar to CodeQL, it finds vulnerable code that matches a certain pattern, but without parsing. Like CodeQL parses the underlying source code, validates types, analyzes include files and whatnot. SemGrep is much more lightweight. Think of it as a dependent grep, where you're running multiple grep queries one after the other to ensure some kind of dependencies. More lightweight in CodeQL, as it does not require compilation, but it cannot reason about variable types. So it's lightweight, but less precise, which means that the underlying patterns need to be more precise for it to actually work. If you're looking at static analysis, also to summarize some of the best practices, I have kind of written up the 8 laws of static analysis that we can look at. And these kind of highlight some of the limitations and some of the advantages of static analysis. First off, you cannot check code you don't see, which means that if you're running a static analysis somewhere in a company, right, it must fit into your build system. You must be able to integrate the static analysis into the build system to actually work on the code that you're interested in, which sounds much easier than being done, right? Because there's like 4 billion build systems out there that are all very, very complex. And an academic prototype may support Make as a simple build system. Who has tried compiling the Google Chrome source code? No brave soul? Interesting. 0. Who has compiled parts of Android? 0. Interesting. Now, both Android and Google Chrome are known to have a massive amount of different kind of build systems. But it's not just Google, also Microsoft and Facebook. It feels a bit that the developers there are being paid a bit too much, so they feel overly creative, and every time they create a new software, they also invent a new build system. So sadly, instead of using existing build systems, Make may be a bit dated, but there's Ninja and other build systems that are fairly well developed. They invent a new build system just for the new software that they are using. So if you want to run your static analysis on their code, you have to support this new build system. There's now like 30 or 40 different build systems, actual build systems out there that are a pain to support. So you can't check code you don't see. The second law of static analysis, you can't check code you can't parse. Which means that, like, who has taken a compiler class? Okay, about a third or a quarter. What language did you write a compiler for it during the course? For what language? Or what language? What toy language? Go ahead, just shout it out.
It was called Alpine.
Alpine? Okay. What was the language related to?
What do you mean related to?
Like what kind of language was Alpine? Like C, like Java, like Python? Functional? Okay. Cool. Who else?
It was for me, Python.
Mini Python? Yeah. Nobody C? C++? Yeah?
It was like a C-like language that was developed like 40 times.
Okay. Was it hard to write the parser?
We used COM402 to parse it. So there were some tools where you can just write how to parse it.
Okay. Did you have bugs in your parser?
I don't know.
Likely yes. What about you?
It was a very big Java file,
Uh-huh.
so after ensuring that the Java file was complete, then it was easier for us to create the parser. But still, creating the Java file was...
So you had to create the grammar file? Okay. Yep. What about Alpine? Parsing. Functional is simple, right?
Yeah, the grammar file was getting it wasn't that long, but still quite a bunch of rules to actually.
Yeah. Okay. So one of the things that you, like, if you ran test cases of your colleagues or written by your colleagues, when I took the compiler class, we shared test cases, and this showed interesting differences between the parsers. And that's the main lesson of the second point here. There's, if you look into the C world, C++ world, there's Clang, or the LLVM framework, there's GCC, there's about 50 versions of Clang. There's different, there's the Microsoft Visual Studio compiler, there's Intel compiler and so on. There's the language specification, which says what should be compiled, but each compiler and each version of the compiler and each setting of the optimization flags of the compiler kind of selects a dialect of the language. And there's a lot of different dialects out there that are somewhat mutually incompatible with each other. And in a static analysis, you have to write your own parser in many cases, which means that you have to follow the right dialect. But maybe you've developed your static analysis for the Clang framework or the Clang universe, whereas your customer may be working on embedded systems that still use GCC. Right? So your static analysis will not run on code that has been compiled by GCC because your parser will just fail. Right? So the very first step of your static analysis, just to extract the information that you need to run the tests, will already either segfault or create some weird issues. Right? So this you cannot check code you can't parse. It must parse real code. Third point: not everything is implemented in C. Right? What do you think Firefox is implemented in? What language do you think Firefox is implemented in? Rust. Cool. What else? C. Cool. What else? There's at least 3 more. C++, yes. What else?
Maybe some Scala?
No. Sorry. Sorry, Martin. What else? You mentioned the first part and JavaScript, yes. What else? Assembly is another one. Those are at least the languages that I know, right? So we are at, what is it, like 5 different programming languages. I know that they are using Python as part of the build system to create some dependency files, right? To auto-generate some code during the build process, right? So it's a 6th language. This is insane, right? Your static analysis will likely support 1 programming language. But in a real system, there's a lot of programming languages that interact with each other, making this really, really difficult. Also, when your system detects violations, the developer may decide that this is not a bug, right? I don't want to fix this because it's a feature. Also, not all bugs matter. Like if your tool finds 500 bugs, should the developer fix all of them? Well, the developer has finite resources, and they will have to decide which ones to fix and how to prioritize, which ones to fix first. So you need to give a priority to some extent. There was a question that I forgot, sorry.
Yes, sorry, no. Before you said that static analysis depends on how you compile it, which component you use. But we saw earlier that like SEMgraph was like not doing like not information, so I'm a bit confused about that.
Yeah, so SEMgraph has a huge advantage, right? It doesn't care. Like SEMgraph, these are general statements, right? SEMgraph doesn't have any kind of type information or variable information or control flow graph information or other details, so it's really shitty. But it works on everything, right?
So static analysis is also often done after completion. No. Because I don't understand why you can parse and why you depends on the code and the...
So CodeQL must compile to LLVM bitcode and then runs on top of this compiled bitcode. It takes a lot of time and it forces you into the LLVM framework, right? Same as LLVM infer. If you're compiling code that has been compiled with GCC before, you may not even be able to compile. Right? So CodeQL is a static analysis that requires compilation to extract all the necessary information or build this knowledge graph, right? Where SEMgraph is just like grep on steroids a bit. Right? So it's a bit of a range, and I'm trying to highlight the range. Good question, though. Good. False positives matter, right? We have to reduce the developer burden. If the developer has to look at 40 bugs, 50 bugs, 100 bugs for one true bug, they're going to stop using the tool real quick. False negatives matter too, right? If your static analysis tool runs and finds 0 bugs, it's not going to be useful, right? It misses all the bugs that are in your code. Also, what some of the results have shown is that annotations are extremely costly. Right, so the developer don't want to write annotations. And if you look at the Linux kernel source code, for example, it would be infeasible to add annotations to the Linux kernel because you cannot annotate 20 million lines of code. So if you deploy annotations, they have to be lightweight and they have to be gradual. But a lot of industry researchers or industry developers are shedding away from annotations because annotations also add to the maintenance burden. As soon as you have added annotations, somebody needs to maintain them, right? As source code evolves, so source code is being used, a developer has to spend time to update the annotations, right? This is an additional cost, right? Not just developing the source code, but also updating the annotations on the side. Right? That's why developers are a bit reluctant to add these kind of checks. Cool. Questions about semi-automated analysis? Yeah?
When we use linters, like TSLint and things like that, is that also static analysis?
Yeah. It tells you something about your code. Right? Mostly formats, but it could also highlight some code smells, right? It is a form of static analysis. Other questions? Cool. Let's move to automated testing. Let's get these cycles. Let's put these cycles to good use. And as an experiment, or as a new research area in the late 90s, early 2000s, a lot of researchers proposed model checking and symbolic execution, which was considered like the ultimate way of making sure that your code is actually correct. Right? So instead of running the code, which was considered too expensive or too hard, the idea was, let's take the source code that we have, we translate it into a mathematical formula, and then ask a constraint solver to reason about possible violations on all feasible paths. Right? And then the SMT solver or the constraint solver will tell us if this is actually correct or not. Same as for formal verification, we will actually mathematically prove that the underlying code is correct. Now, it comes at a cost, right? This is the ideal case. If we can formally prove that code is correct, we're good. We will never have to look at this code again, except if it's used out of context or if the code is being changed. But yeah, it's a trade-off. So formal verification is the act of proving or disproving the correctness of a system with respect to a certain formal specification or property. So you are defining a model of the software of what it should actually do, and then you're proving that the code that you have written actually follows this model, and there cannot be any violations to that model. So for model checking, you translate code into the state machine, and the model checker then analyzes the state machine so there are no violations possible. For symbolic execution, the engine analyzes program by exploring all the different possible paths. Now, what do you think, how expensive is formal verification? Like, how much time does it cost to verify a certain piece of code? Any ideas or any thoughts? Yeah?
Just a question, are we talking about like a function, or are we talking about several files?
A program. How much effort does it cost to verify an operating system?
It's just not possible.
Let's pick a simple operating system. The simplest possible operating system you could write in a class. Let's say an operating system with 2,000 lines of code. This is like a microkernel, right? It's the smallest operating system that you can write, and all your smartphones use a microkernel to actually validate certain interactions at the highest level of privilege. The secure monitor on your smartphone is a microkernel at like 4,000 or 5,000 lines of code. How much effort does it take to verify 5,000 lines of code? Yeah?
Don't we meet halting problem? Is that verification?
Say again?
Don't we meet halting problem? Is that verification?
Well, you're validating, the halting problem is an issue, yes, but you're validating to a certain model. And as long as you're validating that model, it's fine. But you're only proving that it follows this model and the specification. So you're not running into an issue there. So it explodes, right? What you're hinting at, the cost of verification explodes. Verifying 100 lines of code, this is what you'll do in a formal verification class. And if you're taking a formal verification class, you're going to verify 100 lines of code. Easy. You do this in a class, right? You can learn in a semester from not knowing about formal verification to verifying 100 lines of code. After the class, you may be able to verify 150 lines, 200 lines of code. After doing a PhD, you're going to be able to verify 500 to 1,000 lines of code. And the operating system with 4,000 lines of code or 5,000 lines of code was verified by a team of around 20, 30 researchers over the span of 15 years. Right? And that's the SEL4 effort. It's an Australian team of researchers that verified the operating system and made sure that it was actually correct according to the specification. Now, 4,000 or 5,000 lines of code, give me enough coffee and I crank this out over a weekend, right? So, or a developer writes a couple of thousand lines per month, if you consider sane code, right? I'm not saying that whatever I crank out over the weekend is sane code. But if you work for a month, you may be able to crank out 5,000, 10,000 lines of good code, or reasonable code, plus 20,000 lines of unit tests. But then it takes 30, 40, 50 person years to actually verify this code, right? So the cost is immense of formal verification. It makes sense for highly security critical code because you get the highest possible assurances of the code, right? But cost is insane. Interestingly, there was also a bug recently in this secure operating system. Now, how can this be? If you prove the correctness, how can there be a bug? There can be a bug in the prover, but this was not the case. This is usually validated through mathematical things. Yeah?
It falls outside of the model that was proved.
Yeah, if it falls outside of the model, or let me generalize this, if it violates the specification, like if your specification is not correct. So the bug that was discovered in the secure operating system was due to a misunderstanding of how the PCI bus encodes certain bit patterns when they're being sent, which resulted in a bug, right? Yeah. Other questions? Yes?
I had a question, like where did most of the effort go to, like, for example, translating the program to?
Developing the specification. So the question was, where did all these efforts go to? Where were all these person years being spent? First, developing the proof assistants and proofers, developing the specification, figuring out the abstraction of the different components, because you need to break this down into small and individual components, and then writing the actual proofs. Right. So this was a massive, gargantuan effort. So model checking, translate the code into state machine. Model checker analyzes the state machine. One approach to scale this a bit is bounded model checking. And here the idea is that we limit the scope to a certain bounded model. For example, if you're looking at C code, instead of unrolling the loop an infinite amount of times and proving that for any arbitrary amount of iterations of the loop this is correct, you say, I only look at loop up to 10 loop iterations. So you prove the correctness of the program under the assumption that a loop will not be executed more than 10 times, and in most of the times this is going to be correct. Right? So you're not going to catch all the bugs, but you have a good indication you're going to catch most of the bugs. Right? So it's like a generalization of model checking that allows you to go to thousands of lines of code and not hundreds. Cool. Symbolic execution. Symbolic execution is right in between static analysis and dynamic analysis, or different automation forms, and sometimes it's considered static, sometimes it's considered dynamic. It doesn't actually execute the program, but it kind of analyzes all the possible program states. So symbolic execution is, think of it as the math version of programs, as in instead of having concrete values for your variables. Like if you're programming, each variable has a concrete value at any point in time. This value may change during the execution of the program, but each program variable has a concrete value. Now with symbolic execution, we're not looking at concrete values. We're also not interested in concrete values. Instead, we're just making it symbolic, meaning that they're becoming a symbolic variable that we're going to collect information and then keeping track of them. This allows us to define a set of conditions at given locations, and the symbolic execution determines the triggering input whenever something goes wrong. It allows us to find bugs in applications if we define actual validations, translate everything into a formula, and then ask a constraint solver if things go wrong. On the right-hand side, you see a small piece of code where we make a variable symbolic. If the variable is larger than 0, x equals 14. Otherwise, x equals +1, which gives us a state split between state 1 and state 2, depending on if the initial variable, the symbolic variable, is larger or smaller than 0, and it will become either this variable +1 or 14. Now we can combine the two formulas and actually write this as a combined compound statement with like symbolic variable is larger than 0 and x equals, or symbolic variable is smaller than 0 and x equals the smaller or equal to 0 and x equals that value, right? And I just see in this new slide there's an equal missing. So we're missing state 3 where it equals 0, but that's just for discussion or to visualize the different approaches. So for symbolic execution, some of the challenges that we see is that the bug conditions must be clearly defined, such as, for example, the code would have to have an assert x not equals to 14. Or x equals a certain value or whatnot, or different kind of error conditions that we're interested in. And then the symbolic execution engine tries to invalidate this assertion. So you can take the value in the assertion, negate it, add it to the formula, and then ask the constraint solver for a validating like a assignment of this formula. Now the issue in symbolic execution is state explosion, similar to what was mentioned before regarding formal verification. Like as we are translating more and more statements of the program into formulas, we're making them more and more complex. And either the length of the constraints or the amount of state doubles at each loop iteration. So each time we go through the loop, either we double the length of the formula, because it's like loop variable equals 5, loop variable equals 6, and then the whole state of the loop, or we split the state and validate the two different states. So we're having two different forms of state explosion that just increase the complexity massively. Searching valid paths is kind of crucial, so we have to look for valid paths through the program, and then therefore path optimization has become a key research area, along with pruning any kind of states that are no longer feasible. For those that are looking at symbolic execution for the first time, this will be very complex and very hard to understand. So let me try to walk through an example so that we can actually look at this in a bit more detail. So this is a function here. It takes 3 parameters, a, b, and c, that are given as input, and those will be the variables that we make symbolic, right? So these are our symbolic variables. Then the function defines x, y, and z. If a, x is being set to -2. If b smaller than 5, then if not a and c, then y is equal to 1, and in any case z is equal to 2. And then we have an assertion here. X plus y plus z is not equal to 3. Can this assertion be triggered? What do you think? So I'm going to give you a hint. Yes, it can be triggered. What are the values? Give me a satisfying assignment for A, B, and C. That doesn't matter. Like a Boolean is an int. This is fine. This is C code. Like we distinguish between 0 and not 0. If it's 0, it's false. If it's not 0, it's true. Yeah? Very nice. Did you look at the slides? Was it easy? You still need to go through the code. You need to understand it. You need to analyze it. And the point is, why I'm doing this exercise is it's hard, right? I don't expect you to do this quickly because you need to go through all the different code paths, and you're pretty much doing what a symbolic execution engine would be doing. You're trying to analyze and look at all the different code paths and then try to satisfy those. So let's look at what a symbolic execution engine does step by step. We've got the code at the top right. We set x to 0, y to 0, and z to 0. We do static single assignment, so each variable at any point in time in the program will get an index, so A0, which gives us two cases, right? So we're looking through the program, we're looking at the second line after the assignments. The assignments are not yet symbolic, so we continue. And here we're seeing that A is being read. A is being read, so A is being a symbolic variable, so we have two cases. Either it is either it is false, either it is true. Sorry, we are looking at the true branch first. So it is 1 or not 0 in any case. Then we continue through the program. The next condition we're looking at is B. So we're looking at B0 is smaller than 5. If this is true, we go through the next condition, not A and C, which if it is true, we see that y is 1 and z is being set to 2. But the SAT solver will tell us this is an infeasible pass. Why is it infeasible? Because along this path, we've collected the constraints at the bottom. We have A0 is true, and B is smaller than 5, and not A and C0, right? And if in a logical formula we have both A and not A, we know that the whole formula is not assignable, so this means this is unsat. This pass can never be executed, so there's no valid input that will execute this pass. We're good. Right, one pass handled, a couple more passes to go. We go backtrack, right? It's a simple way to enumerate all the different paths through this program. We go back and set this to false. A and B smaller than 5, and not A and C. We fill in the variables, so x is 0, x is minus 2, y is 0, and z is 2. So minus 2 plus 0 plus 2 is 0. So the assertion does not trigger because 0 is not equal to 3. We're good, right? This pass works out well. Same here, we're invalidating, we're going through the false branch of this condition now. We're collecting the path constraints A0 and B larger than 5. If you look at the variable assignments along this path and fill this into the assertion, we get minus 2 is not equal 3. The SAT solver tells us all good. We move on to the next. So now A is false and x hasn't been set, so x remains 0. We go this pass and collect the condition not A and B smaller than 5 and not A and not C. This gives us a satisfying assignment between 0, 4, and 1. For example, here the SAT solver picks some random values that fit and gives us the correct value where 3 equals 3, and we have a violation of the assertion that we looked at. So we found one bug in this program where we can validate the assertion. And as we continue, we find a total of 5 paths that are valid in this small program without any loop, one of which contains a bug, and our SAT solver and symbolic execution engine has discovered the bug, and we can mark it that, hey, this branch, the A branch, is not being taken, therefore A is set to 0, B must be smaller than 5, so the SAT solver can pick and set B to 4, and not A and C, so C must be not 0, and the SAT solver can just pick C to 1. So 0, 4, 1 is a satisfying assignment for this example. And we've successfully symbolically executed these few lines of code and validated all the different paths. You have access to the animations. Go through the animation again a second time. This often takes a couple of iterations to follow through. Now, this is symbolic execution, and you see how much this explodes, right? Without any loops, we've already had to query the SAT solver 6 times, right? And this is expensive. And this is only a tiny function. For larger functions, it will take a massive amount of time. And if you consider large programs, this will take pretty much infinite amount of times. So concolic execution is a form or a specialization of symbolic execution where we are just encoding the path constraints. So symbolic execution is limited due to state explosion. There are way too many paths to evaluate. So in concolic execution, we are fixing one given path. So we are fixing all the different values in the program that encode the path constraints. So we are encoding a given path. We are limiting the options, and here in this example, we would be fixing A to 0, B to 4, and C to 0, but we've added this force parameter D as an example here, which gives us a way to iterate through the program. First instruction, second instruction, third instruction. 2 plus D is not equal to 3. Therefore, if D is 1, we can violate the assertion, right? So here we leave a little bit of, like any of the variables that are not part of the path constraints can be open, or any values of the path constraints that are open can be looked at by the constraint solver, and then to fix the values and see if we can find any violation. So if you go back to this slide here, we would be, for example, picking one certain path through the program to then see if this can be violated. I added an additional parameter to make this a bit more interesting to look at. Cool? So this is symbolic execution and concolic execution. And now we're going to spend the rest of the time by looking at fuzzing. And fuzzing is a form of an automated dynamic software testing technique. Key concept is to test the program by just throwing random inputs at the program and see if it crashes, right? The idea is that we'll just run the program many times, and if we can create an input that crashes the program, that is a valid input according to whatever information whatever we define as valid, then we have found an actual bug. Runs on bare metal, so this is very efficient. We don't have to abstract any way or form. This gives us a very nice advantage. So we don't have to create complex code constraints and whatnot. We simply create random input, throw it at the program, and see if it crashes or not. This example here was the fuzzer playing Super Mario by creating random inputs that conform to the button presses played through the program, and the goal of the fuzzer was to reach the end, to reach the highest possible value. And at the bottom you see all the different paths that the fuzzer took, so to make sure that Mario doesn't die in between. And you see that the fuzzer has a lot of tries initially early on as we go here through the beginning. And the further we go, the fewer iterations are being executed, because this is where the fuzzer starts modifying stuff until it reaches the flag at the end. So fuzzers are somewhat hindered by control flow and data flow restrictions. So for example, if you're looking at a graphics library or whatnot, the PNG graphic format may define that the first 4 bytes must be PNG, otherwise parsing will fail. Checksums are really, really hard to satisfy for a fuzzer. Compression, encryption is hard to satisfy because the fuzzer creates random inputs, right? The fuzzer defines and creates random inputs, which makes all these obstacles hard to bypass or hard to analyze. Also dependencies. If data between 0 and 4 is X, then data 4 to 8 must be Y, otherwise fail. Right? It's very hard for a fuzzer to satisfy these constraints when it creates random input that is being thrown at the program. And we're going to look through some of these fuzzing obstacles in a bit. A fuzzer should explore the target program, right? The fuzzer should trigger different areas of the target program to see if anything interesting is happening. A bug cannot be found if the underlying code is not executed. Therefore, coverage is essential, a necessary precondition for a bug to be found. Like a fuzzer can only find a bug if it actually executes the code under test. Without executing a given code, the fuzzer cannot find the bug there, right? Compared to static analysis, which could find potential bugs anywhere in the code, the fuzzer must be able to reach it and trigger it. Also, fuzzer should trigger the bugs, which means that just running the buggy code or executing the buggy instructions is not enough, but the fuzzer must supply the correct input so that it violates an underlying assumption. A fuzzer should identify faults. The fuzzer should be able to detect when something goes wrong, otherwise it's wasted effort. If there's a memory corruption, the fuzzer doesn't detect it, we've missed a bug, right? And a fuzzer should be fast. Speed is key to a fuzzer's efficiency, right? A fuzzer needs to be really, really quick, execute thousands of executions, because in the end this is a zero-sum game, right? The fuzzer needs to, if you spend more of your compute cycles creating better inputs, you're going to spend less of your compute cycles actually executing the target program. So it's this interesting trade-off between creating better inputs versus running fewer iterations of the target program, right? And you'll have to optimize in this area between the different options when you're creating a fuzzer. The first technique, the first fuzzer that was invented in the 90s, was the black box fuzzer. And a black box fuzzer means that it doesn't know anything about the program at all. So there's the program, and the key idea of the fuzzer is to run the program. The fuzzer creates some input, runs the program, and observes if the program crashes. If the program crashes, the fuzzer sets this input aside and tells the developer, hey, this input here, if you run the program with this input, it crashes. And this is the key benefit of a fuzzer. Right? The fuzzer will give you a witness. And by rerunning this witness, this input, you can create the bug condition again. Which means that now, as a developer, I can take the input that the fuzzer found randomly, he created some random input, run it with the program, and it will crash again. But now I can run it with a debugger, I can run it with extra checks or whatnot, and thereby see what caused the bug and understand more details about the bug. And then the fuzzer just continues with random mutation. Like creates new input, runs the program, creates new input, runs the program, creates new input, runs the program, and just checks if it crashes. Each input is created from scratch, and the fuzzer tests the program again and again and again until we run out of cycles and time. Input generation is random, maybe based on a grammar or based on some other detail that we can add. Maybe we can make this format specific to get past some of the fuzzing obstacles that we mentioned before. But essentially, this is random and independent. Each input is independent from all the others. There's no feedback, no learning, right? So the fuzzer does not learn what good inputs are. So in the end, it's about moving fast and breaking things. Now, this worked reasonably well in the 90s, but as you can imagine, when programs are more complex, it doesn't really scale, because there's always going to be some blocks that the fuzzer cannot get past, and it's very limited in how deep it can explore into the program. Yes?
How would fuzzers observe bugs that don't crash the program? Like, you expect the program to be...
We're going to cover this in a bit. For now, we just expect the program to crash. Right? This fuzzer only detects programs that crash. We're going to discuss how we can make it more likely that the program crashes, but that's another angle. Right? So a black box fuzzer creates new random inputs, and each input is independent. That's the key value here. Right? There's no distinction between good inputs, bad inputs, and no notion of how well a program is being covered. So about 10 years ago, 12 years ago, a new invention was being made called the gray box fuzzer. And here the idea is that we actually take note which part of the program was executed. So during compilation, we'll simply instrument the program a bit to record, hey, this part of the program has been executed, this part of the program has been executed, or this part of the program has been executed. Think of it as a simple array that keeps track how many times each part, each basic block, each function, each line of code, whatever you choose, has been executed. Right? And this gives the fuzzer some information. This input has triggered this much interesting behavior. And it's kind of a very, as you can imagine, you can collect this information very, very cheaply. It costs next to nothing, right? It's an array of integers, and you increment this array a little bit. At the end of the program, you just dump this array, and the fuzzer looks at this array and says, this is good, this is bad, or whatnot. Which means now you can collect this information across many executions. Now, if you take an input and you modify it a bit, right, you can see if your modification creates new and interesting behavior compared to some kind of global behavior that you have. And that's the key difference. Right? Instead of making this one shot, where the fuzzer has to create 64 kilobytes of random data that triggered a bug, which is 2 to the power of 64 kilobytes, 1 over 2 to the power of 64 kilobytes, as in highly, highly unlikely for black box fuzzing. For gray box fuzzing, the fuzzer has to push the input step by step, byte by byte, closer to what you actually expect to trigger the bug. So you can make this a gradual improvement where the fuzzer step by step keeps modifying the input and sees if the modified input reaches new code areas. It will keep this input and keep modifying this input. So it's like a multi-step approach where gradually you reach interesting behavior. Most common feedback that is being used are coverage profiles, where we keep track of what areas in the code have been covered. This can be basic blocks, so we keep counters for basic blocks or counters for edges. The instrumentation for edges or basic blocks is similar. Essentially, edge-based instrumentation is a bit more detailed, a bit more fine granular, and gives you sufficient information to distinguish interesting use cases. Question?
Yeah, in the case of gray bugs, I would be worried that you could only find one bug and only go through this one and not find the others, while in black box you can
You're not doing just one pass. You're having different, like you're usually having a set of 50, 100, or 1,000 different inputs, and your optimization goal. So this is like an optimization where you're trying to maximize coverage across different areas. Maybe this input pushes coverage, improves coverage of this part here. So essentially here, let's say, in this example, for this edge, we have seen 15 iterations. If n input creates 16 iterations, we set it aside. If the purple edge is being increased, we set it aside. So each time an edge increases, we set the input aside, and then the fuzzer circles through all the interesting inputs and keeps mutating them, right? So the fuzzing process becomes, I take one of the inputs from the queue, create 1,000 mutants, out of this starting seed, starting input, and modify each mutant slightly. Right? Do one iteration. Here I changed the 5th byte, here I changed the 100th byte, here I split it apart and merge it with another one, and so on. Right? And if one of these mutants then increases it, we'll set the new mutant aside as well. And this gives us like an exploration of the different areas in the program, and allows us to quickly explore. So it's like a gradual gradient descent kind of search towards different areas in the code. Cool. Did I answer your question? So how do we generate inputs? Right, I already alluded to this a little bit. Not all inputs are made equal. There's different kind of inputs. I quickly explained mutation-based generation, which is there's no specification needed. Everything is considered a binary blob. We modify 1 byte, we modify 2 bytes, we modify 4 bytes, we modify 8 bytes, we delete 8 bytes, we place random values in there. There's different kind of bit flips, changes and whatnot that we just randomly try. It's fast, portable, and scalable. We can also add some kind of grammar-based generation, where the developer will first have to define a specification, but this can make fuzzing much simpler, as in, for example, at the beginning, the first 4 bytes need to be PNG and a 0 byte. Right? So this can be extremely simple to then bypass a check that otherwise would prohibit the fuzzer from finding any bugs. And this allows the fuzzer to be much more directed and more efficient at generating inputs. Mutation-based input generation can be subject to feedback-guided scheduling, not necessarily purely random, but highly biasing towards certain areas. So, for example, const value comparison, compare instructions between data and constants can be extracted and added to the fuzzer. Input to state correspondence. Do input bytes directly correspond to certain control flow decisions, and then the fuzzer can try to directly mutate those. Coverage feedback as reward system, and coverage feedback as an objective feedback for a genetic algorithm. So there's different kind of optimizations for feedback to tailor and steer fuzzing towards certain areas. So using just mutation, you can improve the exploration quite a bit without actually having to develop full grammars. The benefit here is that you don't need to tailor to a given target. You can just grab the fuzzer, compile it, run, and go. This is pretty much what you will explore in the exercise session this week, allowing you to set up a fuzzer for a set of different programs and thereby actually try to find interesting bugs. Input generation is more targeted and will create less redundant inputs, as in you can somewhat follow the format and specification of the program and thereby limit the chuff that you get, right? Any chuff that you would otherwise throw away. The validity of the inputs can be enforced or sampled and thereby improved. It's not just limited to binary representation. You can also say, oh, I expect certain input values or whatnot, and thereby improve this. Cool. So there's two different forms, mutation-based and grammar-based. Grammar-based works best if you have some time to encode the grammar. Mutation-based is a good starting point. Sanitization. This question was asked before, right? How do we detect faults? What do we do if the program doesn't crash? Right? We only detect a bug if the program actually crashes. Fuzzers explore the program, possibly triggering bugs in the process. If you are unable to identify the underlying bugs, then the fuzzing process is useless. So sanitizers are fault detectors and reporters that verify the security policy at runtime, and ideally they will tell us, hey, you have now triggered a bug. Go tell the developer to go fix it. For sanitizers in practice, they detect a lot of violations, but may be imprecise. So they may be missing some violations. Again, this is a trade-off. You've heard about memory safety before, right? Enforcing memory safety for C would be great. This would be a great oracle that tells us whenever we've hit the buffer overflow. But this would come at a fairly high price. And we don't want to pay 2x performance overhead for running these checks to find 2% more bugs than in another scenario, right? So this is a trade-off. How often we will trigger this bug versus what the additional cost of the sanitization actually is. An ideal sanitizer would detect bugs as soon as they occur. An approximation could be CPU exceptions such as segmentation faults, timeouts, division by zero, integer overflows that can trap. Right? So this is a good example. If there's an integer overflow or a division by zero, depending on how you set up your architecture, it will trap and just terminate the application right away. Now, what we use in fuzzing is usually sanitizers that are being added during the compilation. So as we're compiling the program, we're adding slight little checks, for example, for each memory dereference, for each memory write, for each memory read. We check, are we writing to a valid memory area? If not, we're terminating the program. So these are like small bits of code that are added to each memory read or each memory write that the program would do. In the example of spatial and temporal memory safety. So address sanitizer, for each memory deref, it adds a little check. Memory sanitizer, for each memory read, it validates that the underlying memory has actually been initialized. There's other sanitizers, for example, for language-specific behavior, such as undefined behavior, or concurrency for thread interleavings and whatnot. LLVM sanitizers can be applied to source code during the compilation of the program. Code is instrumented with checks at every possible location, as I just mentioned. So for example, before each variable access or each memory access, the compiler would add if the address is smaller than the beginning of the object or larger than the end of the object, it would report an error. There's also sanitizers that operate without compiler-based instrumentation, such as Valgrind, QASAN, RetroWriter, whatnot, that support binary-only programs. But we're not going to cover them in much detail. For any kind of sanitization that we are doing, we need a model and abstraction or policy of the expected behavior. How do we model logic or semantic bugs? It's extremely difficult, right? To actually understand a semantic bug in a program, we would need a specification of what the program is actually supposed to do. For a PNG image parser, this should look like an image. But what should the image look like, right? What's the correct decoding of the image? How can we ensure that all the decodings are actually correct? Most specification is human readable but not machine readable. So maybe we could ask ChatGPT for help, right, to create some kind of oracles. But even there, even if it can find like bugs in small pieces of code, generalizing this to large and extensive source spaces is fairly expensive and probably way too slow for fuzzing. Because again, any cycle that we spend on querying an LLM, we would not be spending on fuzzing. Same as with adding extensive checks, right? The cost of querying an LLM model, if there is a bug or not, would likely exceed any kind of budget we have for sanitization. So this would likely be way, way, way too expensive. So to identify faults, crashes are a certain or good indicator, but not all bugs crash. Sanitizers help us detect faults according to a certain policy, such as memory safety for ASAN, undefined behavior, the thread interleavings and whatnot. These are all different kind of sanitizers that we can add. Typical classes of bugs have existing sanitizers, such as for memory corruption, as you will also see in the exercise session. Real-world systems are complex. security critical bugs can manifest as non-corrupting logic bugs, which are extremely hard to find. So this is an unsolved research problem. How do we create specifications that we can leverage during automated testing, right? So it's an interesting research direction I want to push forward to. There's likely some room for AI-guided bug detection, but it needs to be done very, very carefully in a space where it is beneficial, doesn't have too many false positives, finds real bugs, and is cost-effective. Right? So it's an interesting issue, and the question is if this will actually happen or not. Some closing remarks. Right? I've gone through a lot of different analysis today, so a lot of different classes. So just to give you a little bit of a scale and a couple of metrics that you can look at, I created this table so that you can at least compare a bit, right? Formal verification gives you the highest possible guarantees, but it doesn't scale, right? And then you have individual steps, amount of false positives, amount of false negatives that you get, that you can trade off. And in the end, you'll have to find a niche that works for you and for your project. Currently, what is actually being used and deployed on very large scales is fuzzing and compiler warnings. These are the two main testing techniques that are deployed on a very large scale. Formal verification is an extremely narrow niche. If you have high assurance needs for your software, you can go through formal verification, but it comes at an insane cost. Fuzzing, compiler warnings are very cheap and scale reasonably well even to large software. Code will inevitably contain bugs. Testing or automated testing focuses on techniques to discover as many bugs as possible before the code is actually deployed to the users. Manual testing involves the developer in writing test cases, oftentimes using some kind of static analysis to fine-tune and whatnot. Formal techniques such as model checking or symbolic execution give you strong guarantees, but they come at a massive cost. And they are very limited due to state explosion in how complex the code can actually be that they analyze. Fuzzing is extremely powerful and has become the status quo. There's still research being done there, but it already has discovered tens of thousands of bugs. And sanitization is an integral part of fuzzing to serve as an oracle when we actually detect interesting issues. That's all that I had today. Thank you for your attention, and I'll see you folks around next week.